I'm Ryan Crooks, and this presentation is Methods to Map or Translate Meaning Through Modes of Sensing. The intention of this presentation is to provide an entry for beginners into interactive environments using simple, logical methods with the Arduino microcontroller. Although there are many combinations and possibilities, this presentation will give you an easy starting place. Architects and designers often talk about designing with the senses. However, this is almost always a passive activity, relying on the innate characteristics of materials, not the active introduction of sensory stimuli and cues. The following will provide ways to actively include the senses into designs. Again, this is not meant to be comprehensive, but a good start. There are many examples throughout history of using the senses, especially those related to touch in design. Alvar Aalto was especially skilled at providing sensory prompts. Most often, these were manifest through the touch of the arm and hand on handles, rails, and furniture. The exquisite texture and craft of his detailing creates a richness beyond many other modern architects. Phillippe Starck is another designer who actively plays with the senses through his architectural, industrial, and furniture designs. Here is a chair that he's designed with Cartel and Autodesk using artificial intelligence to create the most comfortable chair with minimal material. Although the seat itself seems common, the splayed legs, back, and vestigial arms provide hints of the possible comfort of the chair. The Palazzo Medici Riccardi in Florence is a famous example from history that uses the sense of touch in its facade. The rusticated base provides texture and undulating forms, affording visual interest as well as a sense of strength and perhaps seclusion. Although the building is now a municipal structure, the landmark was home base for one of the most important families in Italy. The Camden Bench is a notorious piece of street furniture that tries to stop people from using it for too long. The angles of the seat and the changing angular top ensure people will not sit, lay, or lounge on the bench for very long. This street furniture shows how design and the use of the senses can effectively change people's behavior, although not for the better in this case. Mapping with multiple thresholds approaches one-to-one mapping, but instead of matching the levels directly or indirectly of one sense with another, there are discrete boundaries where entirely different results can occur, which is very powerful. However, if it is desired, it is possible to create output with distinct magnitudes of stimulation instead of gradual increase or decrease, as with one-to-one. At the heart of using technology, specifically a microcontroller, is the conditional statement. If that occurs, then this happens, or if that input, then this output. Sensors provide the input, and actuators provide the output, all regulated by a microcontroller. The conditional statement makes the use of the senses through technology possible. Binary mapping is the most basic use of the conditional statement, off and on. If there is no signal, then this occurs, but if there is a signal, then this occurs. Using binary mapping is a great way to provide a sensory indicator of the presence or lack of presence of certain conditions or information, and its use is clear and definitive. One-to-one mapping is a great way to translate one sense to another, providing equivalent amounts of stimulation as received in a different form. This direct relationship is effective, but providing an indirect relationship between the input and output, or the greater this sense or information, the less this other sense, is also very useful. Mapping with a threshold is similar to binary mapping. However, using a threshold allows the tolerance of one stimulus within a limit, then beyond that limit something else occurs. There are many applications of this, especially when monitoring the built-in natural environments where certain elements are always present, but action is not taken until there is a greater abundance of these. Mapping with multiple thresholds approaches one-to-one mapping, but instead of matching the levels directly or indirectly of one sense with another, there are discrete boundaries where entirely different results can occur, which is very powerful. However, if it is desired, it is possible to create output with distinct magnitudes of stimulation instead of gradual increase or decrease, as with one-to-one. There are many different senses that can translate to other senses, whether as an alternative form of communication, an enrichment of the environment, or a form of entertainment. Although this mapping can be used for individuals with disabilities, everyone can benefit from the inclusion of the senses in the built environment, especially as we are spending more and more time indoors. The following are examples of what exists and what can exist in relation to the various senses. Again, although architects and designers claim to encourage the senses in their designs, most focus almost exclusively on the visual. Vision is an important way for us to understand the world, but it is by no means the only or best way. Here are precedents and possibilities for other senses. Touch really is many senses. As such, the examples are broken into multiple modes of touch. The first form, called touch, is the simplest, just nerve endings. The second form is pressure. This comes from the Meissner corpuscles and the hair root plexus. Cold thermoception occurs with the differential of temperature at the Krauss end bulb sensor throughout the body. Heat thermoception occurs with higher temperatures above a certain limit in the group C nerve fibers. Itch is a sense produced by histamine-inducing irritation of unmyelinated C fibers. Proprioception is a very complex sense experienced through the Ruffini corpuscle end organ. The senses of tension and stretch are very similar. However, tension is sensed through the Golgi tendon organ and stretch through the muscle spindles. Vibration is sensed through the Meissner and Pacinian corpuscle end organs. Equilibrioception is experienced via the vestibular system centered at the inner ear. Hearing is not only important for hearing, but also spatial understanding. Although it is difficult to use technology in the conveyance of taste, the senses of sweet, salty, bitter, sour, umami, and possibly fat are easily given through food and drink. Smell is another complex but accurate sense that is able to pinpoint types of molecules through olfactory receptors and sensory neurons in the olfactory epithelium. Although this presentation is downplaying the sense of vision, it generally is considered the most important sense. Translating information to another sense through an Arduino microcontroller relies on electronic sensors and actuators working in combination with conditional statements given in the program. Although some sensors and actuators are more complex, most sensors and actuators receive or generate signals along a spectrum, usually 0 to 255 or 0 to 1023. This makes mapping senses much simpler than first assumed. Now we will review many of the sensors and actuators available, starting with touch. Capacitance sensors, like those on smartphones, are able to sense touch along a surface. Contact switches are binary sensors that sense simple touch. Load cell sensors measure mass. Thermometers and humidity sensors approximate temperature experience like the cold and heat thermoreceptors in the human body. Both the infrared proximity sensor and the ultrasonic rangefinder measure distance but are good for approximating proprioception. Most of the infrared and ultrasonic sensors can only measure in one dimension. However, when placed in groups of two or more, these sensors can provide a mapping of 3 dimensions. Flex sensors measure the amount of bending of an object. Muscle sensors monitor the amount of strain in a muscle at work, and tensiometers measure the amount of tension in or between objects. Tensiometers measure tension either mechanically or electrically by sending electrical signals through a material and measuring the change. Vibration sensors usually measure the amount of vibration through a single or 2 plates. Accelerometers measure the rate of acceleration in 1, 2, or 3 dimensions, and this information can be used to calculate rate of rotation, velocity, and orientation. The tilt sensor provides the degree of rotation relative to gravity. The touch actuators provide different forms of movement to approximate different feelings of touch. DC motors rotate at different speeds clockwise and counterclockwise. Stepper motors rotate in both directions in small, precise increments of movement. Most servos don't rotate more than 180 degrees, but they have a potentiometer on board that provides the actual position of the motor. Linear actuators move in one dimension and do so with quick, forceful movements. Flexinol and similar materials are called muscle wire because they work like human muscle, contracting with the introduction of electrical current and relaxing without. Vibration motors are direct current motors that are eccentrically loaded. The off-balance load provides movement perpendicular to the motor axis. Sound sensors measure the vibration of a medium that reacts to continually changing air pressure created by sound. There are many different types of microphones, however most rely on magnets to measure the sound waves. There are several that use piezo elements, which is a surface that creates and transmits electricity under degrees of deformation. The piezo element is usually small and circular, but it is possible to use large sheets of the material to sense sound. Interestingly, sound actuators are similar if not identical to the sound sensors. Speakers are similar to many microphones in that they rely on electrical currents and magnets. However, speakers create sound with the vibration created with electrical signals rather than creating electrical current through vibration. Piezo elements can be both a microphone and a speaker, which can create an interesting opportunity with the interaction of input and output. Both taste and smell are senses that detect various chemicals and compounds. Electronic chemical testing mimics the way we determine taste and smell. Although these tests don't actually taste or smell the compounds, identifying and indexing them with our perceptions of the chemical's characteristics allows us to understand the flavor and smell of elements without using our nose or mouth. Taste and smell actuators are very limited. Standard food and drink provide taste, yet there really aren't any current ways to produce taste electronically. However, smell has some limited possibilities, such as heating an oil infused with scent and agitation of a surface or powder that carries the scent. It is also possible to introduce perfumes and other fragrances mechanically. All electronic visual sensors measure change using characteristics such as light, color, or pattern to determine visual presence. Photocells measure the amount of light that is present relative to absolute darkness, measured as 0. There are many different forms of machine vision, but almost all of them require an electronic camera and software to establish what is captured by the camera's lens. Many versions of machine learning are getting very sophisticated, relying on machine learning and AI. Although vision is considered one of our most important senses, there are limited visual actuators. Other than lighting, monitors and projectors are our only contemporary forms of visual actuators. Nevertheless, electronic lighting controls, whether for illumination, entertainment, or communication, have become extremely advanced, and monitors and projections provide extremely high definition and can assume various forms to approximate three-dimensionality, such as those so-called holograms. We will use an Arduino Uno microcontroller to develop software sketches and implement the sensors and actuators. Arduino is a very good choice because the software is based on the beginner-friendly processing language from MIT, open source and public domain scripts, huge and helpful user base, and the very inexpensive hardware. The Uno is probably the most popular microcontroller in Arduino's catalog, providing both a 3.3 and 5-volt power source, multiple analog inputs, and digital inputs and outputs, some of which include power width modulation. In addition, sturdy board and minimal size make it perfect for prototyping. However, there are many other Arduino models available. Although Arduino is certainly not the only platform available, it has boards for any project. There are boards with Wi-Fi and Bluetooth capabilities, others with larger numbers of inputs and outputs, some with microprocessors providing advanced computational abilities, others with onboard accelerometers, and some that are diminutive and flexible to provide portable and wearable designs. The Arduino, in combination with a breadboard, jumper wires, sensors, and actuators, allows for quick prototyping. Other sensors and actuators can be exchanged or replaced in the following examples with no or minimal changes to the code. Although the examples show specific equipment and configurations, you can easily change it to suit your needs. First, we will look at binary mapping. The code, called a sketch in Arduino, is very simple, reading whether the input is high or low, that is, on or off. Then, when the input reads high, the output is also high, or on. When the input is low, the output is low, or off. This phrasing makes it very easy to provide the opposite, where when the input is off, the output is on. This code, based on the example sketch button, uses two pins, one for input and one for output, and the conditional statement is clearly represented in the lower orange box with if high, then high, else low, meaning any other condition is considered low or off. Arduino's interface changes the color of the code to describe the purpose. Here is the layout for the example. Note the 5-volt current and grounding provided to the LED, which is the output, and button, which is the input, through the power rails on the white breadboard. It is important to understand that the 5 holes in the individual numbered rows, or terminal strips, on the breadboard are wired together on either side of the center divider. Next, we will look at a direct one-to-one relationship. This Arduino sketch, which is an example file in the Arduino IDE called knob, is a very clean, direct relationship between the position of a potentiometer or knob and a servo motor. Turning the knob in one direction turns the servo motor in the same direction, like a remote control car. The potentiometer gives an analog signal, so it interfaces with the Arduino on an A0 pin. Notice the potentiometer or knob is attached to the analog 0 pin. The servo is attached to the digital 9 pin, and the sketch provides a map that correlates the potentiometer's 1024 positions with the servo's 180. The sensors and actuators can easily be substituted to create new combinations depending on a designer's intentions. Here's the layout for the example. The orange lead transmits the knob's position to A0. The microcontroller translates the information, and it sends the knob's position to the servo via the 9 pin. Note the potentiometer and servo required 5 volts of power provided along the power strip. In addition, it should be understood that the 3 grounds on the Arduino are equivalent or interchangeable. Next is an example representing the threshold condition. This is another example sketch provided in the Arduino IDE called knock, which listens for a moderate signal and illuminates an LED when a knock occurs. The piezo provides a continuous varying signal, but only when it hits the specified threshold of 100 does the light go off. Again, other sensors can replace the piezo because the simplified spectrum of 0 to 1023. The piezo input is on analog pin 0, and the LED output is on pin 13. Notice the threshold given in the orange box. If desired, the threshold can be moved to 600 or higher for a greater signal required to set off the light. Like the piezo, the LED can be replaced with another actuator such as a buzzer or flexinol to provide a different output. Here's the layout for the thresholds example. Notice that it is not so different to that given in the one-to-one example. The switch representing the piezo element in the sketch requires a 5-volt power source, whereas the piezo would not, although both require to be grounded. The final example represents thresholds. Here I have altered the previous example, adding a second LED to provide a third condition. The second LED, which can be replaced by some other actuator, is placed on pin 8, whereas the other elements remain in place. In addition, I have replaced the single threshold at 100 with 2 thresholds, one zone between 100 and 900, and the second above 900. Note the changes in the orange boxes. Between 0 and 100, nothing happens. Between 100 and 900, a red LED illuminates, and 900 and above, a green LED illuminates. The simplicity of the coding allows the conditions to be changed and updated, adding more thresholds. As long as the values don't overlap, there isn't a problem with adding more statements as such. This thresholds layout shows similar wiring to the previous threshold layout, except the additional LED and the switch representing the piezo has been replaced with a potentiometer. The potentiometer is perfect for the prototype because it provides precise inputs to test the various thresholds. As with the other examples, the LEDs and potentiometer can be replaced with other sensors and actuators with minimal or no changes to the code, in most cases. The interchangeability of sensors and actuators and the simplicity of the Arduino platform allow for hundreds of thousands of possibilities to express information through actuators and the senses. It is important to have a clear story or thesis to ensure the best use of the senses to activate a space. That is all. Thank you.